Well, good afternoon, everybody. We're going to begin with this second roundtable of the afternoon to discuss the relations interface between humans and computers. We have two speakers that are going to talk about the first one, investigator Victor Martinez from the University of Valladolid, and he's going to present the project that they have developed regarding a web navigator, but geared for people with severe disabilities. And after that, the speaker, Teodino Freire from the University Espírito Santo of Brazil, will present a line of investigation and work he's been working on regarding electric wheelchairs, robotic wheelchairs, which include that also can interact with the environment. So we'll have the chance to listen first to Victor Martinez, and after that, Professor Teodiano. I hope that you will find the presentations interesting. So whenever you're ready, Victor. Thank you very much. As you said, my project deals with designing a web navigation tool for people with severe disability. To begin, what's a interface, a human computer interface? Well, it's a communication system between the brain and the environment, which doesn't need normal things such as the nerves and muscles, peripheral nerves and muscles to operate. So that is to collect a certain signals, the P300 signals, which are usually use EEG to record the cerebral activity of the user. Given that it's a method which is very invasive, it's not invasive, it doesn't require any sort of surgical intervention. It's easy to use, and it's very low cost. Here in the picture, we can see a user of the application, the little hat with the electrodes, and I'm going to talk about this device. The people have a common disease, which is multiple sclerosis. Multiple sclerosis is an autoimmune disease which affects the nervous system. It's the most common in the world. After the first symptoms appear, 60% of the people lose mobility. In some extreme cases, it can be terminal. This illness is characterized, as we can see in the image, by producing a series of swelling in the neurons, which can lead to a broad range of symptoms such as motor problems, cognitive problems, and psychiatric problems. As a result, the purpose of the study is to provide a web navigation tool which is quick, intuitive, and independent for these sort of patients, aimed at people that have severe disability. The population group that we studied made up of 5 healthy control individuals and 16 patients with multiple sclerosis that we recruited in the State Reference Center of San Andres in Rabanero and Leon. In the picture, we can see the structure of the application we developed. As I said, first we acquired the signal through a hat that it contains electrodes to register the encephalogramma. We detect potential, the control signal, which we're going to talk about. And finally, we interpret or translate the commands and offer feedback to the user. The acquisition of the signal is made up of a series of electrodes, in this case 8 electrodes, which are the most frequent to record the P300 signals. These are through voltage reflections which occur in the cortex, which produces a signal 360 milliseconds after this occurs. The stimulus can be visual, it can be audio, or it could be sensorial. It's an exogenous signal, and as such, we're all able to generate. It doesn't require any training to be able to control it. It's a natural signal issued by the brain after receiving a stimulus. It's 365 hertz, and we can reduce the diffusion between the electrodes. How do we generate these? Well, the commands are given through the oval paradigm, the oddball paradigm, It has to do with a matrix, in this case, a speller matrix. We light the rows and the columns in a random way. All the user has to do is to select the command, in this case 1, and every time the row 1 and the column 1 light up, it'll generate a P600 in the cortex of the users. In measuring these potential, we can distinguish what row and what column the patient chose, and as a result, the intersection. In this way, we can find out what the intent of the user is. Since we experimented with a web navigator, complete web navigator requires many commands. We developed, or is made up of two matrices, our application, which have different functions. The matrix on the left is a small matrix. It's called the navigation matrix, aimed at used for navigating through the web. And you see there's a series of you can scroll up, down, left, and right. You can refresh the page. It's a home page, etc. A series of numbers between 0 and 5, which I will later explain, and various navigation commands where the keyboard on the right, this is much bigger, 9 by 5, so it's harder to select a command. It's fluid, but it's helpful to fill out forms, to write emails, etc. It's made up of all of the letters of the alphabet and symbols that are used in internet, such as the @ or low dash. To detect these mistaken signals and to distinguish what the user wanted to select, we have to process the information. It's made up of two parts, the extraction and the characterization. The first part, the extraction of characteristics, is aimed at obtaining certain information which identifies the encephalogram of the patient. In other words, looking for these signals. It's made up of 3 blocks. The first one is the potential occurs at 360 milliseconds. It's a big enough window to be able to detect it, but small, so it's hard to detect the illuminations. Once we detect the illumination, we look at a frequency of 30 hectares. So there's 16 samples which are classified, and to visualize the P300, we have to work with the averages of each segment. Within the classification of characteristics, the input are the 16 samples, and it tries to determine whether the illumination exists, the 360, or whether the column is precisely this or not. For this, we use LDA algorithm extension, which is called stepwise analysis, which is nothing more than a selection of these characteristics. It's based on random characteristics, and it fills out the set according to an input criteria. The input criteria in this case is that the p-value is less than 0.1. Then we evaluate the p-values, and we carry out retro analysis and make sure they comply with the output criteria, which it has to be greater than 0.15. This algorithm continues until we have the maximum number of characteristics, which would be 60, or until there are no more characteristics that comply with this criteria. The purpose of all this is to determine the command that was selected by the user. However, the matrix will always light up. It's a synchronized application, so that even the user may want to read the website. In this case, they won't be reading anything, but if they had a Wikipedia page and they wanted to read this website, the matrix would light up, and it would continue to select commands in a random way because the user can't select them. So for this, we need to require the level of attention of the user, in this case, through a threshold. The threshold was determined by average to convert this application to detect when the user wants to select something and when the user doesn't want to select anything because he or she wants to read a website or watch a video. The reason why we use this average of 2 optimum thresholds is because the electroencephalogram of the user varies from session to another, depending on the drugs that the patient is taking, or even the way that the patient is using the hat. it can change the signals. The web navigation layer interprets the signals from the first stage and detects the nodes of the website. By nodes, I refer to the hyperlinks, the keys, everything that can be clicked on is considered or treated as a node. In this case, it's going to label all the nodes with a series of numbers. In this case, the numbers between 0 and 5. The numbers that are on the matrix, the navigation matrix. This code length will vary depending on the website, given that not all the websites have the same number of hyperlinks and nodes. And this increases the fluidity of the application. Also, there's a buffer on the upper left of the screen, which serves as a feedback for the user, given that it shows what the user has selected, the numbers entered, and it shows the potential entries, the selections that the user could enter given based on what the user's already entered. We'll show this in an image. When the user enters the number of characters that are necessary for a hyperlink, the hyperlink is automatically entered to save time. I also highlight the labeling is voluntary because the labels could make it more difficult to read a website. Here we can see the image, how the labeling works. In this case, the user in the top left entered a 0, and all the nodes that begin with 0 turn green, and the other nodes stay gray. To evaluate this application, we used 3 different things, 2 calibrations and 1 evaluation. The first session, we calibrated we evaluated the calibrator and the weights of the classifier for each user because they're not always the same. It varies from patient to patient, and to calibrate the threshold. And we do this by asking the user to select a series of symbols and then to ignore them. In this way, we can see the attention span of the user and to put the threshold in the middle. In the second calibration session, we calibrate the threshold again to increase its robustness. And then a third session where we ask the users to do 2 different exercises, navigate in Wikipedia, enter a hyperlink and scroll, and then to read to see how the threshold works, whether they select things when they should, etc. If we don't reach a 70% precision in the calibration, we discard the user for the evaluation because they won't be able to select the commands adequately. So it would make no sense to evaluate the application with this patient. These are the results of the calibration sessions. A table, which is a bit big, but I'll just mention what it's about. In red, these are the users that didn't exceed the 70% threshold that I mentioned, and so they couldn't go through the evaluation session. This means that their latency is too variable. It doesn't happen at 360 milliseconds. It takes place too late, and it's not properly identified. This could be caused by attention deficit, which could make it difficult to pay attention to the visual signals. I also want to highlight that the control subjects, which were down below, they all had 100% results, so the classifier a priori worked correctly. The second evaluation in red, these are the ones that patients weren't able to finish the task. These are only patients with multiple sclerosis. In the yellow color, the success rate is above 80%. And the green is 100% success rate. In the case of multiple sclerosis patients, the threshold works better than the classifier. In addition, 3 of the users had a general precision of 100%, so they did it perfectly. And the control subjects, the threshold precision was perfect. In general, 3 of them did it without any errors. To compare this with previous studies, because web navigators of this sort do exist, we're going to mention the following. The first ones, the Caring and Bench, they use a control signal, CPTS, which is endogenous signal. So it needs training to be able to control it correctly. In addition, it allows for binary selections and it requires supervision. to stop the application when the patient doesn't want to select commands. Google is the other developer. This is most used because it uses P300. And the selection of nodes is done just like our navigator with the labeling, but it needs a reading mode because it's asynchronous, and this reading mode isn't flexible, it's rigid. And as a result, the user had a command for X amount of minutes, and during this X number of minutes, the user couldn't do anything other than read the website, making the application much less fluid. For it, For the controls subject, it was 90% says. The next navigator was Blasco, was similar, but instead of selecting through a labeling, tried to use a cursor with selection matrices. The cursors, like we use a cursor such as a mouse, with pixel differences that were very rigid. We could select commands to move the mouse to the right, to the left, based on the pixels. The success rate was 93% in the present study, which we can see here, with 16 subjects with multiple sclerosis. This is a different illness. They had an average 88% precision rate, and with the control subjects, it was 96%. As conclusions of the study of the web navigator developed with BCE, well, the evaluation with the 5 control subjects and the 16 multiple sclerosis patients, here we see the precision rates. The results a priori are better than the previous studies according to the last comparison, but some subjects didn't complete the task. So we have to carry out this with metropholic multiple sclerosis, which is a more common illness in the literature, and there's no cognitive damage as in the case of multiple sclerosis, just motor. And there's a need to improve the classification, given that the classifier works worse than the threshold. The final conclusion is that the threshold is helpful to establish BCA asynchronous web navigators that can distinguish between the attention span of the user, so that they're not constantly selecting the commands. And that's basically it. Thank you very much for your attention.
At the end of the 2 presentations, if we have time, we will do a Q&A session. Now we're going to give the floor to Tio Freire, who will give us a presentation about a working group in which they are developing a very good role on the field. I hope you like the presentation. I'm sure it will be really interesting. First of all, I would like to thank the ONCE Foundation. They have supported us with these events for many, many years. I always participate as the group that we have in the University Espírito Santo in the city of Vitória in Brazil. What I wanted to do is to present to you some applications that we have created to command a wheelchair through brain signals. Also, the person on the wheelchair with these brain signals will be able to turn on or off the television, the radio, changing channels, modifying or changing the volume. 21 PhD students that are working in our group. And the work that I'm going to present to you show how we've been able to fine-tune some of the techniques of brainwaves working in a regular environment. Of the use of the vowels and different techniques that there are advantages and disadvantages to both systems that we can discuss at very
responde em liberdade por homicídio qualificado. Senha não se conforma com a lentidão da justiça, já que até hoje a data do julgamento não foi marcada.
Só que eu ainda tenho outro animalzinho.
Tem novidade na escola. Agora tocamos em todos os programas. Eu sou presente do mundo. Eu que mando na escola. Será que essa ditadura vai longe? Sim, não vai se perder. Agora é para contar com a guerra para a tua casa, Bahia. Já e ainda mais. Já sobre TV 40 polegadas leve são sobre por apenas
special techniques that I will mention later on. I also want to tell you that this is based on the state of the art. The P300 has been used, as Victor presented yesterday, and we use it to choose the divide within the range of action of the person that we want to turn on and or off. We are using it very much. It works really well with many different devices. We prefer to use the visual potential, but we want to be sincere because a lot of people cannot do it. These P300 potentials are not of general use. Not everyone has it in a way that can be detected with the current available techniques. So a lot of people cannot use them. So we've decided to use the SSBPs because people are like a resonance box. So if you show them a certain situation, your brain responds with a fundamental frequency. And it seems to be more efficient. Otherwise, we're suffering the problem of visual fatigue. We are using this SSBP. We've included the mastication movements, and we are incorporating the encephalogram results so that the person can move the wheelchair and control the devices within the range of action. And I'm talking about people with severe disability, because if someone has enough mobility as to use a mouse, a computer mouse, we do not need to use this type of device. He is more than capable of choosing the device. So I'm talking about a person with no fine mobility, so that they cannot control the mouse of the computer. The paradigms that we're using are the following one. The person sits down, they use a helmet, a commercial but in this case, also we use these electrodes, but in this case we're using this marketed one that is easy to wear.
Responde em liberdade por homicídio qualificado. Célia não se conforma com a lentidão da justiça, já que até hoje a data do julgamento não foi marcada.
Aí não tem. Não tem. Fiquei, cachorro. Sim. Só que eu ainda tenho outro animalzinho.
Tem novidade na escola.
Agora vai tocar música em todos os intervalos. Eu sou presidente mesmo. Eu que mando na escola.
Será que essa ditadura vai longe? Sim, eu sou o trabalhador do SBT. Agora é voltar com a minha na Casa Bahia. Já negocia o vendedor e notícia ainda mais. Garanta já a sua TV 40 polegadas LED Samsung por apenas R$ 1.999.
Chair. Mastication changes the paradigm. Later on, we will see a diagram that shows this in a better way. We have 4 devices: a lamp, a radio, a fan, and a TV. There is a wireless connection. Everything is done from the chair, from the wheelchair, moving the eyes, the eyebrows, and with mastication movements. Thanks to this SSBP, this is the English acronym. Also, in the upper part of the slide, we show the electrodes. We are using 12 electrodes to capture the brain signal. Well, finally, we're only using 2 to detect SSBP, but we're using 12 electrodes because, as Victor did, we are using this system to capture the brain's signals in the occipital region. We use 2 frontal electrodes to determine the horizontal eye movement, as well as the electromyographical signal that it is generated whenever you move your eyebrows. These are some experiments. We have had a previous research done with regards to the frequencies that we can use for SBP. You're seeing on the slide the wheelchair, the tablet. Some wheelchair has some sensors and computers. Sometimes they are industrial computers and sensors, and all of his potential is incorporated on the wheelchair. And these are the frequencies that we've used on these experiments: 8, 11, 12, and 15 hertz that were used on previous studies that are easier to detect its full potential, especially if they are low frequency, although there is a problem with this, because if they are low frequency, they generate a lot of visual fatigue. The one with more potency, they produce less fatigue. If they move up a signal of 8 hertz, it is produced, and then we'll see the harmonic ones that come from the eyesight. We have some lights, some LEDs that are sparkling, and we infer where are they looking at, and everything is coded. If they're looking up, they want the wheelchair to move forward. If they are looking to the right, they're moving to the right. And if they're moving downwards, the wheelchair stops moving. There are many mathematical algorithms behind all of this. As Victor said, we have a clear strategy for all the protocol on how to do the recruitment or the selection of the different commands for the wheelchair, the characteristic of the wheelchair. We have to classify the time frameworks, 8 milliseconds in our case, that it is not giving good results. It's better if we only use 2000 milliseconds. It's a very long time, but the accuracy, it is much better. These are the strategies that we've used. And in this slide, we have the diagram. The person wears the helmet. The helmet takes the electromyographical signals of the face muscles. They also get the electromyographical signal of the eye and brain signals of the axis that are captured with the electrodes. Then the user decides whether if they want to control the wheelchair or the devices within its range of action. And when they use the devices within this range of action, they use the eyes and the eyebrows to command these type of devices. If mastication is done, then those commands are for moving the wheelchair, whether forward, backwards, right, or left. And that is the full diagram. We had less volunteers than Victor did on his work. We have 8 disabled people suffering multiple sclerosis, cerebral palsy, etc., etc. And we notice how these devices do not work with 100% of the patients. Some of them obtain a 100% result, whereas others only obtain 87% when doing the mastication movements. Also with the eyebrows, some people got the 100%. People got very bad were even. So the systems that we're showing to you here, we want to be very honest, they don't operate 100% correctly.
Sobre responde à liberdade por homicídio qualificado. Célia não se conforma com a lentidão da justiça, já que até hoje a data do julgamento não foi marcada.
Change depending, for example, on the emotional condition and the mood of the person, on
Fiquei, meu cachorro. Sim,
brain signals, not
só que eu ainda tenho outro animalzinho.
we have been able to get results in these lab experiments. The brain signal is the most complicated signal to characterize and to recognize. And it's more complicated to work with brain signals than it is to work with myographic signals. Brain signal is much more complicated, so we need to use this SSBP. We have to see the correlation, the maximum MC, to obtain better results. This is a technique that has allowed us to have an average of 88% of accuracy rate for brain signals in time windows of 1 second. This is the multivariated synchronization index.
Tô gravando.
And this is what has given us the best possible results up to date, given the state of the art. We're having a 1 second window, a good average 79% of accuracy rate. When we increase the time frame to 2 seconds, we reach an improvement of 90% accuracy rate, but the system runs at a slower pace. you may end up having a better response time, but with less accuracy. Or maybe you will run the system at a slower pace, but with better accuracy. That depends on what is it that you want to do. These are some of the experiments. We've done several experiments at the university room. We've taken the wheelchair with many volunteers. This is very positive because people are willing to participate, and we have a lot of collaboration agreements with physical rehabilitation clinic, and through the occupational therapies we get many volunteers to participate in our experiments. We have also done, as we show on the previous session, the usability surveys. We think that it is important to get feedback from the users with regards to whether if this system works good or not. But to be honest, these questionnaires, these surveys are very subjective. First of all, the person is using a technology that they do not know how to use it, and therefore they are more prone to give a positive feedback. And if they've been able to move their wheelchair, they always respond that things are very, very good and they want to have that technology made available to them. But we've realized that 10 minutes afterwards, their opinion can change. We've realized that they are very good doing this experiment for 10 minutes, but after 15 or 20 minutes, with the screen blinking, the problem of visual fatigue appears, and therefore they cannot continue on doing. So they say it works 5, but I cannot use it for more than 15 minutes, and therefore we decided to change the system, and we started using the mastication movement, because once they move, they can use the mastication movements to turn on or off the lights or the lamps or whatever. And we stop the SSBP, and the brain has a little bit of time to recover from the blinking line that is very bothersome after 15 minutes. Although we still have to make new experiments with a new system and with more time, including the mastication movements, in order to reduce the blinking light and the visual fatigue. So we have a lot of work to do in the future. We have to incorporate these mastication movements, but what I've presented here as the results that we've obtained up to date. We have gotten good results to detect the eyebrow movement, the eye movement, mastication, with good results, 93 to 95%. For the detection of SSBP, 80% for 1000 milliseconds, 1 second, and better for 2 seconds of window frame. Those are very good results. What we need now is to carry out new experiments with new volunteers using 2 helmets. Only one helmet to turn on or off devices within the range of action, whereas we change helmet to move the wheelchair, but we need a helmet that will be able to do both things at the same, well, not at the same time, but one after the other. And that can be expensive, but very
não se conforma com a lentidão da justiça, já que até hoje a data do julgamento não foi marcada.
There are certain technological issues that are not working. We know that
Sim,
everything seems to be fine to improve. We know how
só
to
que eu ainda tenho outro animalzinho.
responses, but we have to make sure that the system responds to these
Tem novidade na escola.
Agora Apocalipse 2:19. Eu sou presente de Deus. Eu que mando nas portas.
Será que essa ditadura vai longe? Sim, que
answer. Okay, now we can have a Q&A session if you want to ask a question. The topic has been really interesting, and we have the opportunity of having them here to formulate questions. So if you wish to do so, raise your hand and we'll give you a mic. I have a question for the two speakers. First of all, I would like to congratulate them for the good results that they've obtained. But since the first edition of this type of congresses, I've seen similar results in experimental stages. They are very innovative results, but as innovative as they were 8 years ago, but we still don't see anything apply on the market. What do you think that it is necessary to have interfaces in our computer for people with disability that can be translated in efficient devices that can be used at home? I think that what has to improve more is the hardware. Helmets, for example, they can be portable in certain cases, although they normally need a gel or a fluid to make them work. They're uncomfortable. And I think we still have to improve the hardware to register the electroencephalogram of the user before commercializing them. However, I think this year they're going to market some toys. I think they're Star Wars toys with a couple of electrodes without the gel or the fluid, so that depending on how much you concentrate, you can turn on a screen or something like that, as if you had the force in you. But for a much broader use, we still have to work a lot. We've been working with these brain signals for, I don't know, 6, 7 years, and it's true that we are not advancing. We're obtaining repetitive results. I'm convinced that we will be able to advance, but using always binary systems with only two possible commands, either yes or no. Blinking with a frequency, emitting a light with a different frequency, but asking the user, would you like to go forward? And the answer will be yes or no. Do you want to go to the room? Yes or no. Why? Why do we need to use this binary system, this yes or no? First of all, because we obtain better results. You only have to choose yes or not. Once it is yes, the system stops blinking also, and we don't have that visual fatigue. But in this case, we have few commands: left, right, forward, backward, much more complicated than a binary system. Although these type of devices are only for people severely disabled, but we know that ALM people can even move their eyes, and I think it will be better for us to focus on these people suffering ALM, to do a tracking on how they look, how they move their eyes, so that we do not need to use a helmet. And identifying which way they're looking, we will be able to do many different things. Even with the case that I presented here with electromyographical signals, we're changing everything. We want to do everything looking at the direction in which the person is looking, and the devices prices are dropping. That's very good. We have bought two devices to track the eye movements, and they work really well, and they were only costing $80 or €80. And you see if he's moving an eye in that direction or in a different direction from a remote location, and this is what we have to do. I think we have to work that way, because if we continue on working only on the brain signal, we won't be able to advance. I mean, some work has been done in great detail, but from the practical perspective, with this new system tracking the eye movement, we will be able to do some of the things that we've presented here without having to carry anything in your body like a helmet. The system works well without a lot of lightning. They say that it works also outdoors, but I'm not totally sure about that. But, well, as I was saying, everything depends on what you want to achieve. In research, we look for answers, and then we have to put our feet on the floor and say, what are the practical applications of this, and how can we do it? Any further question? I did wanted to formulate a question. We will start with Victor. What are you going to be working on in the future? You have presented here a navigator, but are you going to be working with that? Are you going to include other devices? Do you have another strategy? Are you testing other things? Maybe with a different type of device, maybe with a physical device and not only a navigator. In the case of my research group, we have several research lines, but focusing on BCI, we don't have the experience that my colleague has, but the applications that we've developed, for example, an application for controlling domotic devices, we did it with sensorial motor rhythms, which is another control signal that it is endogenous and it requires some training, but worked really good. We also did an application to control a robot with a camera so that it could move right or left in a room. And for the future, I think we're using this domotic application with these motor sensory signals, and in the future, I don't know. I think that for the moment we are going to try to improve the navigator so that we can make a publication. And within BCI, we're not sure about what we're going to do in the future.
The experiments you've carried out, I wonder about the security issue when it comes to doing this. This is usually the first issue when we're talking about wheelchairs, real movements. It's important to take care of security. Well, I showed in the previous version, this is the wheelchair version 4.5. It doesn't detect staircases. This is very dangerous. There has to be a barrier there, which doesn't allow the to fall down staircases. Where there's a controller that's dynamic, which allows the person to move from one place to the other, just by indicating where the person wants to go. This wheelchair will take the person there. It'll avoid obstacles. The user can use the controls. He can stop the wheelchair and say, I want to get a drink of water, etc. This is what we've done it with control strategies. We've done quite a bit of work with the wheelchairs, with the different sensors. Working with sensors that allow the patient to avoid collisions. If a disabled person is going to crash, imagine the problem. We can't allow this to happen. Although the sensors can always give us problems. So we can either use expensive sensors such as lasers. That's one solution. These are available on the market. The price has come down, but they tend to be expensive. They cost about 2,000 euros, and they can detect obstacles very accurately and protect the people. We've worked a lot with wheelchairs. Now we have a strategy, which I didn't present here, but we're publishing it in a magazine. That's to use a technique which, and one of the limitations that the person has to control the direction of his or her eyes. We need to develop a technique where the person doesn't have to move his eyes. Just all the person has to do is focus on the depth of the objects. So by changing the eye focus, just like a camera, you can focus on one object or another, and this way locate them and also detect the light. This is very advantageous because you don't need to change the direction of your eyes. This is a new technique that we're looking at, but of course all this has to be implemented in a system, and if the person is moving, we have to protect the user. It's not like a robot. We always have to protect the person, but the laser sensors is a good solution. Inside it's fine. Outside it's more difficult. At least for the low-cost sensors, it's very difficult. And indoors, we have to watch out for the staircases, downward staircases, because the lasers can't detect them. So we have to establish additional protection to avoid accidents. Well, thank you very much. I want to finish by congratulating you for your work. And in Samuel's question, we've seen this technology for many years now, to using these signals. I think what happened was we created a lot of expectation, and when this technology appeared, we didn't really grasp all the complexity. But over the years, if we compare what we have now with what we had before, there's been a significant change. The problem we had before, everything was unknown. It's a very dense subject. There's a lot of things that need to be tested. But if we look at all the work that's been done, some technology will be discarded and forgotten. but others is useful for specific situations. And this technology, which still hasn't been tested yet, but this is the job. That's the purpose of conventions such as this. I just wanted to add, I think Victor showed here, and we've also detected there's games that are on the market, but these are for people without disability. But when we look at the results with a control sensor like we do, it's the results are 100%. But how has a person with a disability use it? There's additional problems, and the success rate isn't 100%. These are games for children and for family members. It's surprising when you see it, because this is a big jump forward. But this is one of the reasons why, when we collaborate with universities and investigation centers, we should maximize, try and use real users. There has to be a control group, and we can use people without disabilities, but the investigation and work should include the participation of the final users. The final users of these hypothetical products, because otherwise we'll have unpleasant surprises. Well, thank you very much for joining us, and I encourage you to keep working as you are. So thank you very much.